Hello, hello. Um, I am going to talk about move semantics and perfect forwarding. And I talked about move semantics in a previous presentation, but there's more I gotta talk about. So it's kind of like a do-over, and we'll see how I score this time. Um, so getting right into it, let's start getting ourselves the L value, R value vision. We got to have that first before we can get into moving things in C++. So, um, L value is something that has a name like string S S1. That is an L value. Something that's an R value is a temporary and does not have a name, like let's call this a function signature. String is the return value. Foo is its name, and it has no parameters. The string here is an R value. It has no name. It is temporary. Okay, we got that down. Now, next. What's next? What is next is let's look at pre C++ 11 world a little bit, and um, what what we got to do to be able to bind to temporaries and functions pre C++ 11. So we have another function. We'll call it omega. We got a function called omega. Okay. And we want to bind to a temporary. We want to use omega like this. Omega foo. We want to be able to have, nice client code where we can just write stuff on the fly, not have to write anything up in here. And the only way to do this pre C++ 11 was to have a function signature that looked like this: const string reference, right? And yeah, so basically, you could only have const references bind temporaries pre C++ 11. Not very fun. The reason being was, why let mutable references bind to temporaries? They're going out of scope and going to be destroyed soon. So it'd be foolhardy to let the C++ coders be able to do such binding. Else, they'd be manipulating things that are going out of scope and are being destroyed very soon anyway because they're temporary. So don't let them manipulate the temporaries with mutable references. That was the logic pre C++ 11, but there was some demand for wanting to be able to write this type of code here, and manipulate the temporary data returned by foo within the omega function. Okay, um, that is where we get into C++ 11 land. We imagine traveling here. Since we're in a virtual world, nothing really changes when we travel. So just imagine that we're in C++ 11 land now. And what we can do is void, write this new syntax here: void omega string double ampersand. This stands for R value reference. Yes, we can have a mutable reference to a temporary with the R value reference construct. So we can code omega here. We can make it, we can have an implementation for it where it manipulates temporary data, which in our case would be the temporary data, the temporary string returned by foo. We can have our R value reference here bind to it, and within omega's implementation, we can change and manipulate that data. So, good stuff. Powerful stuff. Yeah. And that opened the gate to, or not really opened the gate, but another facet of C++11 and move semantics is move operations, which are done upon R value references. So, and actually, well, they can be done upon R value references and temporary data. They can be done upon R values, whether they be R value references or just stuff like string returned by foo. And the way that you would define them is this. So we got a class omega. Sticking with the omega fun here. It's nice to name our random names with coolness attached. So class omega, and the move operations are move constructor and move assignment operator, and that's going to be omega omega double ampersand R value reference. Even though this doesn't have to be an R value reference, it can be just an R value. And then you would define what you do, and then our move assignment operator, and that's going to be operator equals omega double ampersand. Okay. So what these slick operators do is allow for the moving of underlying resources between same type objects. So let's say we had O1 and O2, right? And each guy has a pointer to underlying data. O2 is, let's say it's an R value reference. So basically, the epitome of R value reference is, here's some data that isn't around for that long. So if you want, you can take its data and steal it, or move it to another object. So with both these operations up here, you are essentially having the object being moved from have its pointer to underlying data be assigned to null, and having the object being moved to having its pointer being assigned to the other object's underlying data, in essence stealing it or having it be moved to. And that is it. That is move operations in a nutshell. You are not having to do what you did a lot of in C++11, which is unnecessarily and inefficiently make an extra copy of the data. Um, you are C++11 guys made it so that you could be efficient and pilfer resources that are quite pilferable because they're temporary and can be pilfered. Okay. That explains move semantics. And now we're going to get into perfect forwarding. So, let me get a fresh layer here. Okay. Let's say we have two functions overloaded, void f, and it takes an x reference. And we have another one, void f takes an x r value reference. Well, if we have another function that calls f within it, void x, and this one is an r value reference too, right? As well. If you call f from here, even if x, this rx temporary, or this x r value reference is binding to a temporary, it's still going to call this function signature. There's no way that C++ has made it such that the value category type, whether it's L value or R value, there's no way that enclosing functions are aware of the value category type. So what C++11 guys did was this. They made it so that if I'm going to call it G. If you had a template function, you could perfectly forward the value category type of parameters using this new little functionality. Forward G G. So if G's value category type is an R value, that is perfectly forwarded to the f function here. Oh, I wrote it a little bit incorrectly. There we go. Okay. So you perfectly forward the L value, if it's an L value, or the R value if it's an R value, to the enclosing function. So if G is an R value, it goes here. If G is an L value, this one's called. And you're essentially gleaning that efficiency boost where these functions are aware of R value references when the parameters are temporaries and make use of move operations. And yeah, so that's that. I'm going to give one more example of how this template um, uh, R value, L value awareness functionality with functions helps. And I'll get a fresh, clean slate here first. So, pre C++ 11, if you wanted to have nice client code like n string as a temporary and x1, which is L value, and have another client instance call s1 and x is a temporary, and different ways to call where the value category type of the parameters were variant. You want to be able to do all these, right? Well, pre C++ 11, you'd have to write every function overload given the differing value category types. And the amount of function overloads you had to write was equal to 2 to the n, n being the number of parameters in the function. So in this case, there'd be 4 different overloads you have to do. With 3 parameters, it'd be 8, 2 to the 3. And just to really see it in action, you got, if you have A being able to have 2 different states, you'd have to do A1 with B1 and do A1 with B2 and then A2 with B1 and A2 with B2, right? Yeah, so you basically you isolate one parameter and then have the other parameters, which in our case is 1, do all of its combinations. Then you have that parameter change to its other state, and then you do the same combinations again. And so, in essence, with 3 parameters, it's going to be C, C1, C2, times this guy. So for C1, you'd have to do all these permutations. For C2, do all these permutations. The total, 8. 2 to the n being the number of parameters. Okay, so, that very plainly sucks. And it's unmaintainable for libraries. And that's what my research tells me. I go on Stack Overflow a lot. So this is what is so nice about doing the template double ampersand thing in C++ 11. And I say template double ampersand thing because it's not the double ampersand within template functions doesn't mean R value reference. It means either an L value or R value reference. So template class class A, class B, and so now n, just to take a look at it, this is doing what the overload was providing, but with a lot less code, much more manageable code. Yeah. So that it's either that amount of code or writing out the four different overloads for the two parameters, or just like I was saying, the two to the n two to the n overloads based on number of parameters. Okay, that's it. I am done. Good night.